maybe I will start. So, part 2. So, as we did yesterday, please feel free to ask as many questions as you wish. It was very nice having many questions yesterday. So today I will do a very small recap because I see a few new faces in the room. And then I will spend a very small time on the d equals 3 case, in the three-dimensional case where the phenomenology is very different from what we will focus on. And then I will start discussing finally the topic of this course, which is BKT for Berezinskii-Kosterlitz and Thouless. And I will do it in 3 steps. The first step, I will discuss how physicists, the physics intuition behind BKT. So I will tell you how Berezinskii-Kosterlitz and Thouless found out about this transition, and in particular a small story I've read from Kosterlitz about the discovery of this transition. And this part will involve discussing a little bit the concept of vortices. And then I will list, this will be not so short, I will make a list of all the models that satisfy a BKT type transition, and the list will be a little bit, will go beyond d equals 2. There will be some examples which have a flavor of a BKT transition. And finally, this was supposed to be this second lecture, but I will start the mass analysis of a BKT. And just to start with the diagram, we will have to work with the following things. We will have S1 valued models, like the XY. And we will see that there will be in relationship with vortices, and more precisely with a Coulomb gas. And they will also be in relationship with another type of models, which are z-valued functions on top of Z2. And so when I will start the mass part, I will give a more precise definition of the vortices that enter the BKT story. And then I will go into this part, which is where the mass proofs of BKT have, are under play. So, small recap to start. What did we do yesterday? So we introduced spin systems. I will not do the full list, I will just do 2. We looked at an S1 valued model, which is XY, and maybe an S2 valued, which is classical Heisenberg. And they are defined as follows. If sigma is in S1 to the power lambda, where lambda is a subbox of ZD, and very soon D will be equal to 2 in this class. The probability measure we looked at was probability for the inverse temperature beta of sigma was proportional to exponential minus beta over 2, sum over I next to j, sigma I minus sigma j square. And I discussed at length yesterday the fact that it's the same as being proportional to plus beta sum I neighboring j sigma I scalar product with sigma j, where this scalar product is in R2 for the XY model and is in R3 for the classical Heisenberg. So we discussed a bit symmetry breaking. I had simulations stolen from the web yesterday, which showed that maybe at very low temperature we can expect spins to order in a certain direction, and maybe this order will prevail in the whole ZD lattice. But the second hour yesterday we proved the theorem due to Mermin-Wagner from the 60s, which it was a long theorem which said that any infinite volume limit of those models in dimension d equals 2 are all rotationally invariant. So let me just say there is no long-range order in d equals 2 for xy, Heisenberg, and all the spin-ON model. Yes?
Yesterday when we discussed the proof of Mermin-Wagner, we did not explicitly use the dimension 2 condition.
Ah, yes, good question. So yesterday, the main part in the proof, the main tool, was the concept of spin wave. And the spin wave was something which was slowly changing direction from the boundary to the middle. And I introduced one spin wave which worked, but this spin wave did fill dimension 2. So when we computed the Dirichlet energy of the candidate that I defined yesterday, at the moment where we computed the sum of gradients psi squared along this grid, the computation really relied on dimension 2. The same candidate in dimension 3 wouldn't give a vanishing Dirichlet energy and the whole proof would collapse. So at least the proof of yesterday really relied on this, and the first comment I will do in 2 minutes is that this argument must fail in dimension 3. And the last piece of recap I can say is that we also defined an easier model, even a much easier, though it took me some time to talk about it. This much easier model was the case where we don't have S1, we don't have S2, but instead we have R-valued spin systems. And this made the process Gaussian. The probability measure was PGFF in a box at inverse temperature beta with 0 boundary condition. This was proportional to exponential minus a quadratic form, which made phi Gaussian, and therefore one can compute everything. And there we noticed a difference. So d equals 1 and d equals 2 are delocalized. The variance blows up in the bulk of a big box in Z1 and in Z2. And in d greater or equal to 3, the Gaussian free field is now localized, meaning the variance remains bounded uniformly in the size of the system. So I think it's a fair recap of yesterday, but if I forgot something, please complain.
Can you tell us where you stole the pictures on the web? Because
Oh, yes. So those pictures I always use, and I noticed they are used more and more. So it's, okay, I always struggle to find those. If you don't find, I can send those to you. But the credit is to Demidov, who is a mathematician. I don't exactly know in which field, but the simulations are fantastic. If you don't find, email me, I will give it to you. So the first, if there are no questions on what we did yesterday, the first thing I want to do is to very shortly convince you, but I will not prove, that the proof by Mermin-Wagner cannot work in dimension 3. And the only thing which does not work is the question you asked, namely, it's impossible to build a spin wave which has vanishing Dirichlet energy. So I will try to keep my good structure of yesterday. So 1.4, symmetry breaking. For this spin system in dimension d greater or equal to 3. So this title goes against Mermin-Wagner, and what is the reason? So the reason why Mermin-Wagner proof collapses in d greater or equal to 3, the main reason is the following fact. There does not exist a spin wave with vanishing Dirichlet energy in minus nn to the power d when d is greater or equal to 3. So what that means is that if I take this big box of size n by n by n, and I look for a spin wave which is 0 on the boundary of this box, and in the middle of the box went the other way around. So I look for a function which slowly interpolates and uses the whole three-dimensional structure to reach a pi angle in the middle. Then whatever I do, I will capture a Dirichlet energy which is at least a constant. So I'm not saying the Dirichlet energy diverges. Here is an easy example of a spin wave with reasonable Dirichlet energy. I can just put a constant field, and at the last minute I change my mind and I put pi. The Dirichlet energy of this is going to be pi squared times 6 or something like this. So the proof that there doesn't exist a vanishing Dirichlet energy uses something I mentioned yesterday but did not prove. The best possible, the function which minimizes the constraints, which minimizes the Dirichlet energy and satisfies the constraints, namely psi on the boundary of size n is 0 and psi at 0 is pi. We know what the best function is. The best function is the harmonic extension in the graph minus nn to the power d minus 0, because 0 there is a value there. And that's the best possible choice. So let me try to draw what this choice is. So I have my pi condition at the vertex in the middle. I have 0 everywhere. And now let me compute what is the harmonic extension of this function. Let me go just one point next to 0. If I want to compute the harmonic extension, I will send a random walk in this piece of Z3. If I reach this point, I get pi. If I reach those points here, I get 0. And just by the transience of the random walk, you know that as opposed to dimension d equals to 2, the harmonic extension has this trajectory has a positive probability to never hit 0 and fly to infinity and reach the boundary condition here. So without doing any computation, I don't know what this value is, but I know that this is maybe less than 910 times pi. I don't know exactly 910, but it's strictly less than pi, uniformly in n. And because of this, the Dirichlet energy of the whole attempted spin wave is going to be at least 6 times this non-vanishing gradient squared. So whatever you do, you will never be able to build a good enough spin wave to apply this relative entropy, Pinsker inequality, and all business we did yesterday to prove Mermin-Wagner. So the Mermin-Wagner proof collapses, And there is even a better reason. So this is the math reason regarding the proof we did yesterday. But there is a theorem which goes further and says not only this collapses, but in fact, the statement of Mermin-Wagner is wrong in dimension 3 and higher. So this is due to Fröhlich, Simon, and Spencer in 1976 in a very important paper. And they prove that if D is greater or equal to 3, there is long-range order at high enough inverse temperature beta, at low enough temperature T, for spin-ON model. And one corollary of this is that there exist infinite volume limits of spin-ON models that are not rotationally invariant in D equal to 3. And they don't do just infinite volume limits. What they prove is that if you define spin-ON model on a sufficiently large torus, so Z3 mod n Z3, then they have a quantitative way of saying that the correlations do spread across the whole three-dimensional torus. So it's something like if you take the average value of the two-point function over I and j chosen around the torus, this two-point function doesn't go to 0 when the magnitude of the torus go to infinity.
For any n larger than 2.
So if this is true for any n even larger than 1, but 1 is Ising, I did the proof yesterday. So it works for Ising, but this is a bit of an overshoot. And it works for xy, for classical Heisenberg. And in fact, for all continuous spin systems with continuous symmetry, which have a property to be reflection positive, and a little bit more than that. They need the infrared band, which needs a little bit more than reflection positivity. So it's a beautiful theorem. I will list a few other proofs that exist, but there are not many. So, so there is a Balaban in the 19s, which applied RG flow analysis on those spin systems to also detect long-range order at low temperature, but as far as I know, this is very hard to read. But could be potentially applied to more complicated spin systems. There is no need of reflection positivity. There is Fröhlich-Spencer in 82 and Kennedy-King in 86, which found other proofs for the XY model, so the S1 valued case. And they used the fact, in some sense, that the Fourier transform of S1 is Z, and this is something we will rely a lot on for the BKT mass analysis later. So this works only on S1. And let me advertise one proof I have with Tom Spencer, the same Spencer as here, 2-3 years ago, which works for XY, which gives a new proof for XY, and also for non-commutative spin systems, but they would need to have some quench disorder. So I will not write it down here. One advantage of this proof here is that it works on graphs which are much less symmetries, so you could have some holes. And this is something we used with Paul Dario in the room last year to prove such phase transition on any supercritical percolation cluster in dimension 3, for example. Okay, so that's all, and this proof uses, maybe surprisingly, links with Bayesian statistics. So my plan is to say nothing more about dimension 3 unless there are questions now, but then I will only stick to dimension 2.
I have a question, but it's about dimension 2, so...
Well, go ahead.
Just what you explained right before the theorem. Does that mean that on any recurrent graph you can do Mermin-Wagner, or is it more complicated than this?
No, that's a good question. So, yes, Mermin-Wagner, I think... so certainly you don't need to have a Z2. So if you were to do, for example, an n by n grid in dimension 2 with a little bit of an altitude, like let me not do a big altitude, but maybe a square root log n or something. I don't know exactly. Then the same proof works exactly the same. So Mermin-Wagner is very robust. You can remove things out of the graph. There is no symmetry. So as long as you have a good enough spin wave, the proof works through. BKT will be much more sensitive to the choice of graph and interaction. So we discussed a lot yesterday the fact that the proof here doesn't care so much about the interaction as well. It works for S2 valued, it works for whatever ferromagnetic choice of interaction. BKT will not work for S2, it's conjectured to be wrong, and will need some specific interactions. Okay, so if there are no questions, let's move to d equals 2. And for a moment, I will stick to the XY model. So 1.5 physics intuition behind or for the BKT phase transition. So, very important will be in dimension d is equal to 2. So we will work on Z2, S1 valued, so this will not work for S2, and it's conjectured to be wrong. I will look at the XY model. Maybe to compensate my small recap, I will define it like that. In a finite box lambda inside Z2, I will view it rather as a collection of angles, theta in 0 to pi, and this will be proportional to exponential beta. So those are the nearest neighbor interaction, and I will have cosine theta I minus theta j. And maybe I will start with a provocative drawing. So yesterday I did not write, but I claim that it is believed that if I look at the free energy, of this model, which in statistical physics tells you almost everything you want about your model, it's conjectured that this will look something like that. Well, I don't know the shape exactly, but okay, I don't know exactly the shape, but the point is that it's C infinity, conjecturally. So this is quite peculiar for phase transitions. More precisely, if this is the transition point of BKT that I will explain in a minute, this is supposed to be analytic here. And in fact, up to a certain temperature, by cluster expansion, I guess this can be a... Okay, maybe this is not completely believed that you can get analyticity up to a certain point. getting analyticity all the way to the critical temperature, this is supposed to be difficult. And I think it's also believed that it's analytic after the critical point. But here, there is a phase transition. This one is now proved. So you're not going to have something analytic. But the conjecture is that still you transit from one to the other in a C infinity way, which is a bit crazy. So that's the math and physics understanding of this transition. But this BKT transition, which was discovered in the 70s by Berezinskii and Kosterlitz and Thouless together, this was an independent discovery. They were awarded the Nobel Prize in 2016, not Berezinskii because he had passed away before. And I looked at the Kosterlitz video about when he received the Nobel Prize, and he told the following story, which I really liked. So he said that around the early 70s, he wasn't sure where to go for a postdoc. It looked very complicated, but eventually, I think he was partly sad about it, but eventually he went to UK to do a postdoc with Thouless. And then he explained what the postdoc was about. And Thouless told him there is something very strange, because if you look at liquid helium, it seems there is a phase transition. So apparently Thouless, from what I understand, was looking at the free energy of liquid helium, and the free energy was looking like that, which is not quite C infinity, by the way, but Thouless found a free energy which that seemed to be a point which was not analytic. And then Thouless... Sorry?
These are experimental data of Thouless?
Thouless experimental data, yes. So in his lab, I don't remember where in UK, there were people playing with liquid helium, and they had this experimental data, maybe for the specific heat. But still the derivative of C infinity function is still C infinity, so I have no clue how it can look like that. But and Thouless told his postdoc that they seem to observe a phase transition from the viewpoint of the free energy, despite the fact there is a mathematical theorem by Mermin and Wagner which tell you there is never long-range order, there is no phase transition. So how come they spot a transition that mathematicians disprove the existence? So Kosterlitz was as puzzled as Thouless, and they understood that there is a more subtle phase transition, which goes as follows. So maybe let me remove this non-C infinity. They understood that as you move the temperature, there is a critical point, which is now called the Berezinskii-Kosterlitz-Thouless point, which is such that Mermin-Wagner theorem is correct, so they did not disprove Mermin-Wagner theorem, that was correct. The proof of yesterday still resists to this day. But when temperature is high, there is exponential decay of correlation. So what does this mean? You take lambda n go to infinity. The xy measure is in fact known to converge to a whole Z2 measure. The fact we have S1 value, there are correlation inequalities which prevent us from taking subsequential scaling limits. So there is a well-defined infinite volume limit. And in this infinite volume limit at beta equals 1 over t, if you take 2 points in Z2, and you measure how do they talk to each other, if you take x and y in Z2, cosine theta x minus theta y, or if you prefer sigma x scalar product with sigma y, measured in this infinite volume limit at inverse temperature beta, this is exponentially small in the distance between the two. So there is a constant which depends on the temperature times the Euclidean distance in Z2 between X and Y. And in fact, proving such a statement at high temperature, here, say, this is very easy. When you have a high temperature, compact valued spin system, it's a standard property in the beginning of a master class to prove that that things decorrelate exponentially quickly. There are many proofs of this. Cluster expansion would be the hardest, but there are some Markov chain type of proofs that are quite easy. So it's easy to identify this. And I suppose at the time of Berezinskii-Kosterlitz-Thouless, it was easy to predict based on Mermin-Wagner that the phenomenology will not change as we go to the low temperature regime. Only the zero temperature will catch something different with symmetry breaking of the ground state. And they predicted that in fact, the story is different. At some point in the low temperature regime, correlations are polynomially decaying. So in other words, with the same setup, I take an infinite volume limit, which is now at a small temperature. They predicted that cosine theta x minus the angle at a distant point y should behave like 1 over the Euclidean distance between those two to a power which is a critical exponent which will depend on the temperature. And this, of course, in the 70s, but maybe even more in the 80s, this is something that that was very close to conformal field theory, namely to try to spot what those critical exponents are. And just to make a comparison with the Ising model, the prediction by BKT led to the following picture. So let me first draw the phase diagram of Ising. So if I look at Ising in dimension d equals to 2, and there is beta, then there is the beta which has been computed, say, by Polyakov or Kramers-Vanier. So there is a critical beta of Ising, which is explicit on Z2, and which is such that there is exponential decay. Okay, let me keep the temperature. I will always go back and forth. It's a bad habit that I have. So at high temperature, this is exponentially decaying. The fact one has exponential decay all the way to the critical point is called sharpness of the phase transition. So this is much more difficult to establish. The fact there is long-range order here up to the critical point is basically by a definition. And the power law decay is only at this point. Power law decay. And for Ising, it is known that sigma x, sigma y at the critical point behaves like 1 over x minus y to the power 1/4. If now I go to xy, the prediction by BKT is that there will be a critical point which will be smaller. So the fact it is smaller is intuitive. It's because the S1 model will create more disorder than the plus minus 1 model. And there are even some, I think one can gain a factor of 2 by a result of, I think it's Eisenman and Simon. And so the exponential decay here we'll go all the way to the critical point for the simple reason that this critical point is defined as the limit, the barrier between polynomial and exponential. So there is no sharpness in that sense is clear. And they predicted polynomial decay in this whole regime. So in other words, there is a whole line of critical models. Each of these has its own critical point. And for a reason which is not very clear to me, if someone knows, I will be very happy to learn this over the tea break in 1 hour and a half. Sigma x scalar product with sigma y, which is the cosine between the two angles, at the BKT point for xy is believed to be 1 over x minus y to the same 1/4. Maybe it's a coincidence, maybe there is something deep, I don't know between the two.
So you are saying that function alpha of t interpolates between what and 1/4?
Yes, so I can even draw the function alpha of t for you. So now I regret t, I may have preferred the beta, but so if there is BKT here, it's conjectured to be exactly 1/4 at the critical point. And it's intuitive that as t goes to 0, the exponent must go to 0. And there is even an upper bound. So there is an up. So alpha of beta is known to be less than something like 2 pi divided by beta. So with the temperature, it's linear in T, good. Actually, I didn't know, but this graph is much better in T. So this upper bound was proved by McBrien and Spencer. It goes to 1/4, yes.
So T is 1 over 8 pi?
No. A good point, it's an upper bound.
Yeah, but you draw it, okay.
It's an upper bound. The truth is elsewhere, but I can give you a lower bound. Okay, the lower bound, this one would be better in beta. Maybe the lower bound is like this. And the lower bound is a work I did with Avelio Sepulveda a few years ago. And the gap between the two curves is the gap is less than exponential minus a constant 1 over t. So for very low temperature, this linear shape is did I do?
The upper bound is sharp at the critical point.
So the real curve, what is now in right the final curve?
Goes for 1/4. Yes.
Yeah, just a second. I need to be sure I did not mess upper and lower bounds. Okay, let me write, and then we'll correct my statement. So theorem is that sigma x scalar product with sigma y for the xy model in Z2 inverse temperature beta. This is less than 1 over x minus y to the power, I never know if it's 8 pi or 2 pi, but it's something like that. And this is McBrien-Spencer. And the result we... no, okay, sorry. Okay, I will have to change everything. So the lower bound is the most interesting, and this one is due to Fröhlich and Spencer. And the exponent is something like 2 pi divided by beta 1 plus little o of beta. So they lose a little bit something in the lower bound. And the result I have with Abelius-Sepulveda is here. It improves a little bit on this. And it's for the villain model, so it adds something like that. So that's the true inequalities. And now I have to transfer these inequalities in terms of exponents, which I'm pretty sure I did everything wrong. So I'm saying we have 1 over distance to the 2 pi beta a little bit more than beta, less than the correct exponent, which nobody knows how to compute at the moment, alpha of beta, which is less than this. So I guess it means that this is a lower bound. I made everything wrong. And this is an upper bound. So let me keep the mistake and correct it in the blackboard behind.
And it doesn't go through a force, right, at the critical point?
So hopefully neither the lower bound nor the upper bound go to 1/4. Yes. Otherwise it was a little bit suspicious.
But in fact, Kosterlitz and Thouless, they made a guess for this critical point, which was an estimate, I guess, and there really the bound coincides with 1/4, right? Because they say, maybe not, I don't know.
I think the prediction they make is proved to be correct by Pierluigi Falco for a modified Coulomb gas. So the activity needs to go to 0. For those models, it's just not known what there's no guessed values for the critical point.
But there must be numerical simulations giving a very good estimate of alpha, no?
Yes. Up to 3 digits, and maybe if Slava goes into the business, there may be 8 digits eventually. Yes, I cannot, but yes. I gave you a curve which is upside down with the upper and lower bound. So maybe let me try to. So this is conjectured 1/4 at t BKT. And what did I say? So this gives a lower bound on the right. So probably the linear t is somewhere here. So that would be McBrien-Spencer. With Abelius-Sepulveda, we have something a little bit above. So vortices do play a role. I'm a bit optimistic with 1/4. 1/4 is probably much above. So this is the bond we have with Sepulveda. And then there is a upper bound on those exponents, which is very close to those, but then it kind of diverges before the critical point. And this one would be Fröhlich-Spencer in 81. And I think I could also draw another picture. So Pete, correct me if I am wrong, but there is another proof of BKT which would give an upper bound of 1. So this is 1/4, this is 1, I'm sorry. And this new proof would be by Diederik van Engelenburg and Martin Lies, and also by Eisenman, Harel, Peled, and Shapiro from 2021. And they built on a work by Pete, who is here.
But the bound 1, it's the Simon-Leib inequality, right? I mean, that really doesn't use a height function relation. The bound of 1.
Yeah, that's true, but their proof says there is polynomial decay, which is non-trivial, and the bound the proof gives is what Simon-Leib would give. But I think in this diagram, that's what it would give, no?
I see. Okay.
Because no power law bound would be infinite.
Yes.
So this still says that there is a... So in that sense, it's not quantitative because it's what Simon-Leib is doing, but it's non-trivial that there is an upper bound here.
I see.
Fröhlich-Spencer, it's very non-trivial that there is an upper bound. The lower bound says that it gives some bound on how it can fluctuate. So Thibaut, your question is where the true curve is. Yes. And I will draw one, but it's a guess. It's a complicated one. It cannot be linear by those two works. So it's sandwiched here, almost linear, and then it's known it's monotone. But I don't know what it looks, but that's the true curve.
So 1/4?
It goes to, yes, this yes.
So the conjecture is confirmed.
Well, I don't know if the conjecture started with numerics or, I think, no, I think there are some theoretical argument for this 1/4 here, but it's confirmed by numerics. Okay, I had not prepared this diagram, obviously.
It's better, we will remember more.
Good. Good, so yes, so conclusion of all this is that there is a line of critical models, and the exponents which describe those models, that's a complicated curve in T. So now I want to tell you where does the power law decay come from for this XY model. So where does power law decay come from? So for this, I will make some approximations. So the probability measure of the XY model in a big subbox, this is proportional. This, I have written it several times already, cosine of the gradients of angles along the edges. So the first approximation I will do is something one likes to do in physics. I will do Taylor expansion of the cosine. Then I will discuss at length whether we are allowed to do this or not, but let me first do it. So the reason why I claim I can potentially do a Taylor expansion is that beta is supposed to be very high. I mean the very low temperature regime. So in particular, the spin field will prevent edges to carry big gradients. So on most edges, maybe there will be some weird stuff sometimes, but on most edges, I will have small gradients. So maybe it's not crazy to assume that theta I minus theta j is something typically small. So let me pretend that this measure looks a little bit like, so cosine is 1 minus 1/2 theta I minus theta j squared. And the quartic term and all the others, I don't know how the x to the 6 is called, but all those, I don't look at those. If we were to do RG analysis, we would need to follow the contribution of those as well, but they would put tiny corrections to those critical exponents here. So here I don't put those. I just claim this is something straightforward for those of you who do statistical physics, that I can get rid of this one. This one doesn't play any role. It will just be absorbed by the partition function that I described yesterday. So let me just say that this is in fact equal, once I did this approximation, to exponential minus beta divided by 2, sum over the nearest neighbor, theta I minus theta j squared. Now I will make a second approximation, which is that my angles at the beginning of the day, they were between minus pi and pi. And I will say we are in very low temperature. I can replace minus pi pi into r without too much loss. So second approximation. Let's replace minus pi pi, theta I into this, by phi I into r. If I do this, my Gibbs measure now looks like exponential minus beta over 2, sum over I next to j, phi I minus phi j square. And this R-valued field is the one I discussed a lot yesterday. This is the Gaussian free field. So we recognize the GFF. And now we're in good business. Why? Because if I want to understand the cosine between theta I and theta j, this is nothing. So by my approximation, this is potentially close to cosine phi I minus phi j for a GFF in Z2 at inverse temperature beta. To believe this, one has to believe both the Taylor expansion approximation and the fact there is not much going on angles that are far from minus pi pi. Everything should be very close to 0 because of low temperature, the gradients at least. If I do this, if you believe me with all that, this is something which is very nice because I'm computing the cosine, the expectation of the cosine of something which is just a Gaussian random variable. And this we know how to compute. So cosine of z, expectation of cosine of z if z is Gaussian, is the same as the expectation as e to the iz if z is Gaussian, and this is e to the minus 1/2 sigma squared, where sigma is the variance. So this two-point function, the only thing I need to know to compute it, z2 beta, this is e to the minus 1/2 times the variance of the Gaussian free field at I minus the Gaussian free field at j. And remember, we are in Z2, and yesterday we've seen that the covariance matrix of this was related to the green function of the random walk in Z2. So this is expressed in terms of the random walk, the simple random walk on Z2. And I don't want to do any manipulation here. You've probably heard that the green function of the simple random walk in Z2 involves logarithms everywhere. So you'll probably believe that this variance is logarithmic in the distance between I and j. So this will be e to the minus 1/2 times logarithm of I minus j. And there is a constant here which depends on two things. It depends on how the green function behaves on Z2, and there are some 2 pi or 8 pi that I never know. But let's pretend it's 2 pi. And the variance of this Gaussian free field also fills the inverse temperature as we did yesterday. And the larger beta is, the lower the temperature is, the variance diminishes when beta grows, and the beta is in the denominator here. And if we look at this into the i's, it's 1 over distance between I and j. I don't know why I moved to I and j instead of x and y. And all of this is to the power, okay, so there is a 2 here, so it's not quite what I had before, but maybe this was a 4 pi because I never know. So 2 pi divided by beta. And that's the explanation for a power law decay at low temperature. But that's not why they got a Nobel Prize for. They have something much more interesting going on. Because this prediction would predict something linear in T here. It wouldn't feel anything more interesting in this picture. It would just say maybe the XY model at very low temperature behaves like the cosine of a GFF. And that's why it has power law decay. If this was true, if it was linear, this would be in contradiction with the fact that as T grows, we know there is exponential decay eventually. So there must be some other phenomenon which either destroys this Taylor expansion or makes those assumptions more relevant. So unless there are questions on this first attempt, which gives a fair enough explanation of these exponents very close to low temperature, I will move to a more precise analysis of this. I will be as lousy as I was at the moment I did the Taylor expansion, but I will be a little bit more precise with this step, in some sense. So are there any questions? And that's the step where we will see the vortices appearing. So one way to see the vortices appearing I will try to draw a very low temperature XY model. So if we were to do a very high beta simulation, we would see something like that, to the point that when I look at the gradient of angles between two neighboring points, gradient of angles, which is theta I minus theta j, is well defined most of the time. But now it could very well be that if I keep track of those gradients along a curve, okay, maybe it's a bit long to draw, but I think you see where I'm going. I don't want to do something stupid. Yes, I think it's okay. No. Okay, I think I messed it up somewhere. I wanted to get back on where I was. The point of this is, even if you have a very low temperature simulation of the XY model, it may be the case that when you integrate the well-defined gradients of angles along a large curve, you will spot a monodromy. Okay, don't look too closely at the simulation. It may be zero monodromy, but if I do things well, it could be that edge by edge the gradient is well defined without too much ambiguity, but still as you integrate those, at the moment you get back to where you started, you accumulated a 2 pi, maybe a 4 pi monodromy. What that means, the consequence of this is that d theta is a one form. This should be rather viewed as a random one form and not as a field of angles, as a zero form, as a random one form. In other words, the right probabilistic object is not quite the angles attached to each point, but more how do you move from one place to another, and the gradients you move in this direction is minus the gradient you move in this direction, so you're really in the presence of a random one form. And now BKT, what they asked about is what is the law of this random one form d theta. And there they came up with the following nice explanation, which is that when you have a one form, it may not necessarily be something which is exact. And the picture I have drawn is a one form which is not exact. If you have monodromy, you cannot be the gradient of a function, of a zero form. So what they found out is that this random one form, the fluctuations behind this random one form could arise from two different sources. So d theta, the one form, by the Hodge decomposition. And I will go back to this. In our case, it will be something very simple. You will not need to know too much about this. It's a bit too much of a fancy word here. This one form can be produced out of two things. Either I have a function phi on the vertices of lambda with values in R, and it's called a zero form. It lives on the vertices of my graph. It's a function. And I take the gradient, the discrete derivative of phi, and I obtain a field of angle. This would be a little bit what I have drawn here. There are no monodromies. But it could also be the case that I will produce something with a co-derivative that I will introduce later. And those are precisely the vortices. The vortices produce one forms that are not exact. So a typical vortex would be a one form produced like that, or one forms like this. So the one form would be the gradient of those. So in fact, they would be the same. So all the configurations of angles that look like that, they're produced with a vortex here, which is a two form. So this we will see that it lives on the plaquette of the graph. And we will have d star of a vortex, which will produce different type of fluctuations in the d theta. So what they observed is that xy field has fluctuation coming from zero form and also coming from vortices which have monodromy. And here, maybe I can try to show a picture. So this picture is still stolen from Demidov, but I made a tiny decoration to it. So my contribution in this picture is extremely tiny, but so that's the picture I want to show. So I'm sorry, it's going to be just 1 minute. So I just took the simulation from Demidov of an XY model. I did cheat a little bit there because it's a Markov chain that he is suggesting in his web page. And I did stop the simulation before reaching equilibrium. So I did cheat a little bit. If I was to wait equilibrium, the singularities, which are the vortices, there would be less of those and the picture would be less nice. But the intuition of Berezinskii-Kosterlitz-Thouless that they got from this strange behavior of the free energy in the liquid helium is due to the fact that here, oh, I forgot one here. In fact, I forgot many. Okay, so my contribution is just to single out the vortices, but I forgot zillions of those.
It's plotted exactly. So.
What is?
What is plotted?
So what is plotted is each pixel is one xy spin, which is colored depending on its angle in a periodic way. And this is a low temperature xy model, almost at equilibrium. And what I added is the places where there is a local monodromy, which propagates all the way to another local monodromy. And I just try to draw whether it's a clockwise monodromy or anti-clockwise monodromy. And the physics explanation of the BKT phase by Kosterlitz and Thouless is that those vortices, they always exist at whatever temperature, but the statistics of those vortices will be different at low temperature and high temperature. And what they understood is that at high temperature, the vortices are everywhere in space and are not too correlated with each other. We will see that there is Debye screening. We will even prove Debye screening in a very easy way. And as the temperature drops, at some point the vortices need to cooperate together, and they call the phase transition binding, unbinding of Coulomb gas of vortices. So they noticed that at very low temperature, when there is a vortex, it needs to solve itself as quickly as possible, otherwise it will cost too much Dirichlet energy. And I will do this one computation that they did to explain that there is a phase transition from the viewpoint of the vortices. But if there is any question, so what has never been very clear for me, but it will be very clear in the end of this lecture, I hope for you, is that for the XY model, the monodromy is not completely defined without ambiguity, because I go from a theta I to a theta j. I claim the gradient is the closest to 0, but it's not fully unambiguous. And then I try to spot monodromies this way. We'll have a different model for which this picture will be exact. We will have an exact decoupling of a Gaussian free field and a Coulomb gas, and there the locations of the vortices will be unambiguous, will be very clear. There will be a bijection from the spin system to the vortices field, while here I find it a little bit more ambiguous.
The vortex field is a two-form?
Is a two-form, yes. Yes, it's a two-form. It lives on the plaquettes. It will be defined extremely precisely. Not now, because it's the physics. But I will define it extremely precisely for the villain model, not for the XY model.
And for the XY, you can't define it by orthogonal composition between these two parts, the gradient and the vortex.
So yes, so indeed, so maybe there is a way, but when you have one forms, the Hodge decomposition always works. But here it's the fact it's in minus pi pi is a little bit less standard, I guess. That's why, to me, I'm pretty sure that there is no canonical way to do things. Maybe there are several definitions which would more or less agree at low temperature, but in the villain case, there will be no ambiguity. So, if there are no questions on the picture, I will remove it, and I will do the key computation they've done, which explains the phase transition. So, what they said is that the fluctuation arises from those two possibilities, but this one we already understood with the computation I did on the right. This one is basically the GFF. So this one, in fact, always produces power law decay of correlation. Only this one will be responsible for going from power law to exponential. So this one captures the non-trivial part of the model. And they did the following computation. So the question they asked is how difficult it is it to produce a vortex which is not paired with a close by anti-vortex. So the question they asked is, if I have a vortex and I cannot cure the monodromy of this vortex, what is the Dirichlet-Cost of such a beast in the XY model? So if this vortex is not locally cured, it means that each gamma that I have in Z2 will spot a 2 pi monodromy until the moment maybe I will find a minus vortex, which will be such that paths which surround both will not spot a monodromy. Each such path gamma, if it spots a monodromy, it means that if I sum the gradient of angles along this path, I will see 2 pi. Let me compute what is the Dirichlet energy of such a cost along one such gamma. The Dirichlet energy along gamma is defined as the sum over the edges in gamma of the d theta along the edge squared. And in fact, the best way to do it, the least costly way of doing it, is to spread the 2 pi angle evenly along gamma. So this will be always bigger than the best way of spreading gradients. And what is the best way? If my gamma is at distance k from my vortex, it's the same type of computation as what we did yesterday. So I will have k position along gamma, and each of these positions will have roughly a 2 pi divided by k squared gradient. So the best way is to make this very even and to have 2 pi over k all along. So this is a Dirichlet cost which is up to constant 1 over k. So I computed the Dirichlet energy in this layer, but I need to sum over all the layers around my vortex all the way to the next one, or maybe to the middle distance. So this says that the energy cost of such a pair of vortex so this implies that the Dirichlet energy cost of a plus vortex and a minus vortex at distance m from each other this is bigger than sum from k equals 1 to m over 2 up to constant 1 over k, which is log m. So the energy cost of pairs of vortices like that are logarithmically big in the Euclidean distance between those. And now they asked how many, so question 2, how many such macroscopic vortices can we expect? So the macroscopic pairs of vortices, so I will be in the same box as I used through the course so far, which is lambda n equals minus nn squared. Maybe I will make a bigger drawing. And I want to ask myself how many macroscopic distant pair of vortex antivortex can I hope to find in my system. And here they make an entropy energy computation. They say that in this big lambda n equals minus n squared, there are n-fourth choices of such pairs. So I have n squared choices for a plus, roughly, n squared choices for the minus. So I have n4 choices of pairs plus and minus. But now each of those, if we don't take into account the contribution coming from the rest of the system, they seem to pay an energy cost which is log n. And here, regarding Pete's comment, they were careful on what is 2 pi or 8 pi here. This was important. Though not exact, it doesn't give the exact critical point for this system. So this is the entropy contribution to the system, and this is the energy part. And now you see the classical fight between the two. This is n4 1 over n to the beta. And there are some 8 pi floating around, but they are not exact, those 8 pi's. So you see that if beta is large enough, the energy, it's energetically too demanding to have macroscopic vortices. While if beta is small, you'll see tons of such vortices. So the picture is as follows. If beta is low, beta large, the XY model is e to the I GFF. So it's like a derivative of a function. So something quite simple, Gaussian, plus some plus and minuses very close by. So it's a bit harder to draw. But this is resolved. I don't want to draw it too big because I will mess it up. But there will be many pairs of vortices like this, which affect the GFF, but only very locally. They don't spread those fluctuations very far. They're constrained in a very local way. And this is called the vortex binding at low temperatures. And for plasma experts, this says the Debye screening in plasma physics and all this is not at work in this low temperature phase. And those vortices, they do add a little bit of influence on the exponent I computed before. So in those curves, I first messed it up and then I corrected with the upper and lower bound. The curve we have with Avelio says that those vortices contribute something like exponential minus 1 over beta, so exponential minus beta to this alpha t, which we don't know what it is. So it's not that these pairs of vortices are not visible in the scaling limit. They are still visible, but they have a macroscopic contribution, but it's small when the temperature is tiny. So in other words, this one contributes 2 pi over beta to the exponent alpha beta, and those, they contribute, when beta is large, they contribute exponential minus c times beta. So they are still there in the scaling limit, but they're small. And as T grows, as beta goes down, the low temperature, so beta low, T large, there is still the e to the I GFF. But on top of this, there are many vortices everywhere that are not paired with the neighbors. And each of those produces a vortex potentially at large scale because it's not resolved by local neighbors. So the XY model in the high temperature phase is it's called the plasma of vortices. They produce enormous fluctuations, and those are responsible for the exponential decay. The zero form are never responsible for those. So the BKT phase transition is also a phase transition of the Coulomb gas which is associated to it. And the purpose of the end of this lecture, before I give a list of models, will be to describe precisely what is the probability measure on those and what is the phase transition there. Are there questions? Yes?
You seem to say that the exponential decay results of the presence of all these vortices and a quite sophisticated phenomenon. But you said earlier that exponential decay for large temperature is something easy.
Yes, it's a very good question. So, exponential decay is very easy for spin systems that have a local interaction, nearest neighbor interaction. When I will define more precisely what is this gas of vortices, we will see that this is called the Coulomb gas. This one is in fact interacting with all the others with a logarithmic interaction. So it's a bit like this Coulomb gas that you see in random matrices for the Ginibre ensemble. So they interact with everyone. The interaction is very high. It's the logarithmic interaction. And what the bi-screening is saying is, to me, was extremely counterintuitive at first. It was saying, despite those very heavy interaction at very long range, what I see here is exponentially decaying with what I see here. And this exponential decay is not easy to prove, as far as I know. So, because it's not nearest neighbor interaction. While the XY model, so before we go to this dual picture, the XY model, the Ising model, and so on, they interact only locally. And if this interaction is very weak, if beta is very low, if it is very large, what's going on here will not manage to affect what's going on very far away. But those, even at very, very low beta, at very high temperature, they still have this logarithmic interaction with whatever is at the infinite distance. So this is why the Debye screening is a more subtle phenomenon. But where you are right is that the Debye screening enters the moment where the other model has exponential decay. And in the story I will tell you next, we can use the easy part of exponential decay over there to get the Debye screening over here, which I think is a new proof of this and is a very, very short proof of Debye screening.
When you use the word dual picture here, from what I remember reading about KT, is either you use that theta is d star of something, and then you work with this something, or you say it's d of no, so it's either or. No? You don't say it's the sum of two.
I'm saying it's the sum of the two.
Is it well defined, the decomposition?
Yes, I will have a theorem which will say, for a slightly different model, the villain, the theta field, the angle field, in law will be equal to a sum of two independent objects, a GFF, which is the zero form, and a d star of something which catches the Coulomb gas. And the two sources of randomness will be independent of each other. So it will be very clean.
But in usual physics thing, no, one says either I am vortex phase or no? Or I am remembering wrongly?
I am not saying I am either one or the other. I'm saying we are both.
Yes, no, I understood what you said. I was just saying in what I read, for physics, they say either I am in the dual or the other picture.
So I would imagine in physics they would basically say this part is trivial and we don't even look at it. That would be my guess, because it's GFF. And then they would only focus on this, which is non-trivial. The phase transition is only there, in some sense. That's true. But if you want the probabilistic fluctuation, you still need both. And in the curve I have erased now, most of the curve is actually produced by this one at low temperature. So you don't fully want to forget about it. But BKT soon moved just to this picture because it's the nice part of the phase transition. So I think maybe this explains why you...
I also have a question. Yes. So when we talk about these vortices, we always think that they appear in pairs. Mm-hmm. So by that, are we assuming some boundary conditions that constrain us to, whenever we have a plus vortex, we always have a minus one?
Yes, so that's also a good question. So in the model that I will define next, depending on the boundary conditions you work with, Dirichlet or free, the Coulomb gas that you will see will be either fully neutral. So if you have 5 vortices plus, you will need to have exactly 5 minus to compensate. With the other boundary condition, it could be that the monodromy is cancelled by the complement of the graph. But in both cases, it's very well defined. But free and Dirichlet leads to 2 different ways of looking at it. So I am done with the physics explanation. Maybe I will just say orally that there is a second piece of physics explanation which is important, which is that once they understood this, they did put all this into the renormalization group framework to have a more precise understanding of the BKT phase. And in particular, they managed to understand how the correlation length of the system blows up when we reach the critical point. So I will just say here that RG flow analysis, and this was done, I think, by Kosterlitz, but also by Rosset, Kirkpatrick. It's the same Kirkpatrick as spin glasses and things like that. No, Kadanoff, Kirkpatrick, and Nelson. I think this is in '77. They did a precise RG flow analysis of those systems, and they managed to prove or to guess that the correlation length when T is larger than Tc, so in the plasma phase, should behave like exponential 1 divided by square root of T minus Tc. So this came out of RG flow computation, and it gives a pretty precise understanding of how the correlation length should blow up. And this is a little bit the reason why the free energy should be C infinity. So what I wanted to do now was a list of all the models that satisfy BKT. But I think I will do this next time, otherwise I will not even start the math part today. So maybe I will start the math part and leave the list, the long list of models that fall into this class for next week. So maybe chapter 2. So, mathematical analysis of BKT. And for this, I will start with a few additional models. One of those will be the Coulomb gas, more properly defined than what I did. So 3 additional models. And I will start with a small diagram of what I will do in this section. I spend a lot of time discussing the XY model, but we'll soon move to a close cousin of the XY model, which is called the Villain model, which I will define now. And we will see that this Villain model is very related to a Coulomb gas. And this is the one which describes the gas of vortices. And we'll also see that it's closely related to the z-valued Gaussian free field. And at the moment, I will explain to you one of the proofs of BKT. In all the known proofs of BKT, we have to go to z-valued interfaces. And only Fröhlich-Spencer proof, in some sense, goes back to the initial intuition of the Coulomb gas. So this one goes back, in some sense, to the Coulomb gas. And in that part of the proof, we have Fröhlich-Spencer 81, von Engelenburg-Lys 21, Eisenman, Harel, Peled, Shapiro 21, and those are based on Pitt work in 20. So what I will do now, maybe this I will keep it for the moment I will start the proof of BKT, and I will just introduce those two models to you and discuss those. So let me start with the villain model. So it's a close cousin of the XY. So in particular, it will share the same target space and the same philosophy. So I will use the same notation. So for this villain model, I will take a box lambda inside ZD, but I will only discuss d equals 2 here, but it could be defined on any d-dimensional lattice. And it will be a measure on angle theta I in lambda. So this is my state space. And the probability measure p beta lambda villain of d theta. As yesterday, it will be a Radon-Nikodym derivative with respect to the uniform measure on the angles attached to each point I in my space. And my Radon-Nikodym derivative will be proportional to something which will capture an interaction between the points. And this interaction, if I had the XY model, I had exponential beta cosine theta I minus theta j. It's a close cousin, so it changes the interaction, and instead it chooses the ith kernel on the S1 circle at time t equals 1 over beta between theta I and theta j. So it's a product along nearest neighbor edges of the ith kernel, which goes from this angle towards this angle in the circle. And here, the circle S1 is very simple. There is an explicit expression of the ith kernel, which I will write down right now. So, to compute the ith kernel on the circle, in fact, you just need to know the ith kernel on the real line. And then you need to, if you lift the circle to the real line, you project back. So the villain model on this field of angles in the box lambda is also proportional to a product over I and j. Here is the ith kernel. It's a sum over integers in z, exponential minus beta over 2. The gradient as in the XY model, but now the difference is that I have 2 pi m squared, product I in lambda d theta I. So this function here, I will call it f villain of theta. This function, which is sum over m theta plus 2 pi m squared. This is also called the periodized Gaussian. So why is this a close cousin? If you look at this function when beta is large, you will easily notice that it's you plot that it's extremely close to this one, at least for the small gradients theta I minus theta j. So the low temperature phenomenology of those two models should be very close to each other. A reason why villain will be simpler, there are two reasons. So villain, so that's why I explained here, villain will be very well related to a Coulomb gas. So that's the first reason. And the second reason, so this I want to explain today, I hope I will have time. The second reason is that the Fourier modes of these 2π periodic functions are very simple. They are simpler than the Fourier modes of this one, which are Bessel type functions. Those ones are very simple. The case Fourier mode of a periodic Gaussian, it's an easy exercise to check that this is exponential minus 1 over 2 beta k squared. And here we will see in the next lecture that this will play a very important role. When you do the Fourier transform, as often with Fourier transform, it interchanges the effect of temperature. The beta now is in the denominator, and this will be very important. So the second reason, before going into this, is that the Fourier transform of this new interaction, the closed cousine of xy, is extremely simple and will make our analysis easier. So that's the villain model, and I will play a lot with this one. Before I define the Coulomb gas, let me tell you why there is a link with a gas of vortices. The fact I have an heat kernel over here allows me to see the villain model as a model not only on Z2, so it's not just a model on the vertices of Z2, but I could extend this model in the whole cable graph. I will explain what I mean by that. And the extension to the cable graph became very popular in the last 10 years or so. It started, I think, with Titus Lupu, which identified that cable graph extensions of spin system, in this case the Gaussian free field of spin systems, leads to additional tools like Markov properties and so on, further tools. So this villain model, since it is a heat kernel along the edges, it turns out that I can extend it along the cable, and this will do a Brownian motion on the circle along these cables. And if I do this along each edge of my graph, maybe the Brownian motion here, so it's a continuous stochastic process, maybe it can do 1 or 2 turns or half a turn along this edge. And I look at Brownian motion with S1 valued Brownian motion along each of these edges here. So if I do this cable version of the villain model and I only look at it, I only spot what it does on the vertices, this is exactly this model here. But if I decide to keep all this additional randomness, now I claim that I have perfectly well-defined vortices. And furthermore, going back to your question, they're perfectly well-defined on the faces of my graph. So how do I read vortices? For each plaquette here, I take any starting point, I go around this Brownian bridge, this Brownian motion along the circle, and at the moment I go back to where I started, two possibilities: either there is no monodromy, and I say there is no vortex here, and if there is a monodromy of 2π, I say there is a +1 vortex, If there is 4 pi, I have plus 2 vortex. Minus 2 pi, I have minus 1 vortex, and so on. So if I manage to simulate the villain model in the whole plane, and I claim there is one infinite volume limit, conjecturally a unique one, this is not proof, but conjecturally a unique one, whatever the temperature is, I have a unique Coulomb gas that is associated to it, which is a field of integers on the plaquette of my graph. Okay, so it doesn't yet define the nice probabilistic model on those plaquettes. I will do it right now. But at least going back to the previous discussion, now, given a S1 valued spin model, I have a very well-defined field of vortices.
And no GFF?
There will be a GFF. The GFF comes from all these Brownian fluctuation. They add randomness to the story. And the GFF comes from the part which doesn't produce the monodromies. So there is a Hodge decomposition behind. The part coming from the zero form will be exactly a GFF, no approximation, exactly GFF, cable GFF. And the other part will be exactly coming from the vortices, so this is more a discrete nature, but this will be exact. And this exact splitting is very beautiful, I find. And I think, if I'm not mistaken, it goes back to this work by Rosset, Kadanoff, Kirkpatrick, and Nelson. So, so I need to define for you what I mean by a Coulomb gas. I will do it in dimension d, but we will only need it in dimension 2. So, definition. Coulomb gas on DD, but we'll stick to the dimension 2. But Debye screening and all those things, they are also very interesting in higher dimension. Also for Thierry, for lattice gauge theory, they are relevant in Z4. So I will pick any box lambda inside ZD. But now I have a tiny issue of notation. Either I keep this, or I already point out the fact that later on I will need this on the dual, on the plaquettes. But, okay, it's just not to have a conflict with later. I could also define it on the vertices of the graph. Okay, let me call it lambda bar. So I have any finite box in ZD. And to the points of this graph, and these points will be the faces of the previous graph in a minute. Okay, maybe I will just do the dimension 2 case, and I will make everything consistent. So I will define the field of integers on these faces. So the state space is going to be z to the power the faces of lambda. I will just do dimension 2. So a point in this state space will be q in z to the faces of lambda. Let me draw one example of such a configuration. So maybe I have plus 2 here, plus 1 here, plus 1, and maybe I have a minus 5 over here, minus 1, I don't know, and 0 everywhere else. And now for any beta positive, or 0, I will define a probability measure on this field of integers attached to the plaquette of my graph. So it will be exactly like before. It will be Coulomb. But now it's a discrete statistical physics model, so I don't need to be too scared with a Radon-Nikodym derivative or anything. I can just pick one positive weights for each of these and hope that the sum of those weights will be bounded to have a well-defined probability measure, a well-defined partition function. And the weight I will put here will be minus beta over 2 times q against minus Laplacian of q. So if I do this, there is one mistake. If I do this, it would be a Gaussian free field restricted to take its values in Z. And this was the fourth model I wanted to talk about, but I will delay it to later. The Coulomb gas is much less local. There is a -1 here. It catches not the Laplacian, but the green function. So if you don't like this is also proportional to exponential minus beta over 2, sum over I and j in the placket of the graph, or maybe f and g faces on this graph, of the integer attached to f, the integer attached to g, and then the green function in the graph g lambda at f and g. That's another way to write down my Coulomb gas. And now, answering the questions you asked before, if I tell you about this operator, I would need to be a bit more careful. I need to endow this with some boundary condition. Otherwise, it's not even clear which Laplacian I am playing with. So here, there are two choices. I could do Dirichlet boundary condition, and in this case, there is no neutrality condition on the Coulomb gas inside. Or I could do free boundary condition. Both are well defined, both lead to an invertible Laplacian, but one needs to be careful if it's the free one, otherwise it's not invertible. And this one will be in duality with the free villain, while this one will be in duality with the Dirichlet villain.
Don't have Neumann boundary condition?
I think my notion of free is what you would call Neumann. So the random walk bounce is reflected along the boundary. So this is what you would call Neumann in continuum. So both of these lead to a well-defined thing, but the only difference is I need to change the graph, I need to go to the placket, and I need to invert the boundary condition.
So,
yes.
Do you think this has some Laplacian of GFF?
Ah, yes. So that's a very good question. So indeed, if those were not integer valued, this object here is maybe exactly the Laplacian of a GFF. Yes, and actually this plays an important role. I don't think I'll have time to go into this, but yes, that's a very good point. But the fact I stick to the integers, this is not the Laplacian of an integer valued GFF. Once we go to the lattices, it breaks those change of variables that you would do to go from one to the other. But if it was R valued, and I could also define this would be exactly the Laplacian of a GFF.
So you could see it as the Laplacian of an R-valued GFF condition to be discrete?
I think, yeah, that's right.
Okay.
Yes. Yes, and in some sense, the fact there is the bi-screening for the Coulomb gas could also be viewed this way. Because before putting the constraint to be z-valued, the bi-screening would be obvious. But once you restrict it to the integers, it could kill the bi-screening. In fact, it does at low temperature in Z2, so it's subtle, but at high temperature it doesn't. Are you happy enough with this? You could ask yourself what's the ground state of this model, as I did with Ising. In Ising, I claim the ground state is either all pluses or all minuses. Here, what is the ground state? There is a quadratic form here. So to me, it's a positive one. So the ground state is when this is equal to 0. And pretty naturally, the ground state is just put no vortices whatsoever. Which is natural, but it's a good sanity check. So in the few minutes which remain, I want to state a proposition and to start proving it. I will only do it for the partition function, and we will start doing the math behind those models. So the proposition, so this is a proposition we have with Avelius and Pulveda, but it's basically a probabilistic translation. It's a slight extension of a very nice observation which already existed in Rosset, Kadanoff, Kirkpatrick, and Nelson in 1977. So it's only a proposition in this sense. And the probabilistic content is as follows. If theta is a villain model on lambda, then the one form d theta has the following decomposition. D theta is equal in law to d phi plus d star Laplacian inverse, and there is a 2 pi. Okay, so I realized that there is no chance I will do this in the minutes that remain. I will do something else. So where phi is a GFF on lambda, so it's a zero form. Q is exactly this Coulomb gas here. So it's a Coulomb gas on the faces of lambda. And cherry on the cake, phi is independent of Q. So in other words, to produce a villain field, you first produce a GFF. Independently of this GFF, you produce a gas of vortices like that, which has this long-range correlation because of the green function. This is not at all, that's why this one is hard to prove exponential decay a priori. You take these two bricks of randomness. I will need to discuss next time what do those things mean. We put those together, and this produces the gradient field of a villain model.
It's a discrete gradient. It's theta I minus theta j.
Yes.
We are still on the lattice.
I'm still on the lattice, yes.
Or it's the cable thing. No?
This one is for the lattice one, but it could be complemented along the cable if desired. Yes, this one is discrete differential calculus on this discrete graph. So my 0 cells are here, my 1 cell are there, my 2 cells are there. And I will need to do a little bit of a crash course on differential calculus next time. I will need those. But about that, I must say that when I did learn differential calculus in bachelor, I was very confused with extra derivatives, and it looked very beautiful, but I was extremely confused. And with Avelius and Pulveda, when we needed to know those Hodge decomposition and those in this discrete lattice setting, it all came very clear to me. I suddenly found that must be the way to teach, because everything gets way simpler. And in fact, I even discussed with experts in the continuum, and at some point, those explanations made everything clear even to them, which I will not mention. But I think this is a fantastic way to do a discrete differential calculus. So in the very few minutes that remain, maybe I can write one direct corollary of this. So corollary 1, and I will have many later. Corollary 1, if we assume this proposition, let me compute the cosine theta x minus theta y for the villain model in a big subgraph of Z2 at inverse temperature beta. This we know by Mermin-Wagner of the last course that this is less than a constant square root 1 over log Euclidean distance between x and y. So this is the course number 1. This is the proof by Mermin-Wagner that we had yesterday. But if we believe this proposition, we can do something much better. Let me compute this. This is the same as exponential I theta x minus theta y in the villain model lambda beta. And this I can write it as integrating a one form along a path which connects x to y. So let me imagine that x is here, y is over here, and I will find whatever path gamma which goes from x to y. So I can rewrite this as expectation I, the one form d theta integrated against the path 1 gamma. Okay, my brackets, they don't mean the same thing. This is an expectation, this is a scalar product. I'm sorry. You must be used to this. So if we do this, now I will use the independence. This is nothing but the expectation under the GFF of d phi against 1 gamma. And this is a GFF of inverse temperature beta. This is still there. Okay, this should be here. So this is a beta GFF. And this Coulomb gas is a beta Coulomb gas, but there is a 2 pi squared which pops up in my definition. It just comes from the fact that the heat kernel has 2 pi. There's nothing very fancy here.
It's not 1 over beta. It's still beta.
Yes, this one doesn't have temperature inversion, yes. And the temperature inversion that we have in the Fourier mode, maybe this I can say because I like this very much. This one is at beta. This one is at beta, or depending on the convention, is at 2 pi squared beta, but still very low temperature. This one is at 1 over beta. The fact there is a relation between those two, this is one particular instance of the Riemann theta, of the Jacobi Riemann theta. Okay. Okay, I'm not sure I have the right keywords, but there is a very nice identity which links z-valued Gaussian and z-valued Gaussian of their inverse. And this theta identity is exactly what is at stake in this duality here, and the inversion of temperature is due also to this. If you prefer, this is just Poisson summation formula. It's Poisson summation formula. But this identity turns out to be very powerful when you also play with the magnetic field. And so the Coulomb doesn't, this is still beta, not 1 over beta. So if I use the independence, by independence, this is this times something very complicated that I don't want to write. I didn't even define d star Laplacian inverse. I will do it next time. But the point is, I don't care. If I just want an upper bound, this is the expectation I is something complicated. The expectation of this, in any case, is less than 1. Right? The absolute value of this is less than the expectation of the absolute value. The absolute value of exponential I is 1. So if I want an upper bound, I don't even need to go into the Coulomb gas. This is less than the expectation of this, and this I have already computed before. This is a Gaussian expectation. This is the Gaussian free field at x minus the Gaussian free field at y, and this is exactly the first intuitive step I did in the physics derivation of BKT. So this we have already computed, and this was exponential minus maybe 2 pi, that I don't know, the beta is in the denominator, and then there is log x minus y. So just using this proposition, we get a bound which is much nicer than what Mermin-Wagner gives. it doesn't give a bound in terms of total variation. This would be stronger. But for the two-point function, we have power law decay just like that.
So Spencer and McBrien were doing something of this form?
No, not at all. So but what they do works for XY. And this is more targeted at villain. So what they do is different, but they would also get power law decay. So, okay, so I think I should stop. So what I will do next time, I will start with giving you a list of all the models that are BKT related, even going very shortly to 4D abelian lattice gauge theory. So there are many things that are in this family of models. So I will give a list, and then I will do a small crash course on a differential calculus. We will talk about what is a one form, how to do the Hodge decomposition, very like 15 minutes. And we will use it to prove this proposition and to start going into BKT.
Thank you.
Are there any questions?
So in that decomposition of the villain model, do we get a chance to get some almost sure decompositions? Like right now we say something in law. Can we decompose almost surely the villain model into a Gaussian free field and a Coulomb gas?
So this says that there is such a decomposition.
Okay.
Maybe your question is if I see the villain model, what should I do?
Yeah, like we can somehow really extract one thing and the other.
Yes, and one way to do it is to add additional randomness to produce the Q and retrospectively get the phi. But without adding additional randomness, there is not enough there to really do the decoupling a posteriori.
I don't want to spoil next week, but is the Heisenberg model in Z3 in the list of BKT models?
No. The reason is the Heisenberg model in Z3, the classical Heisenberg, this is understood to some extent by this Fröhlich-Simon Spencer, yes, in '76. Which tell you that in Z3, this system has long-range order at low temperature.
Does it mean that there are no vortices in Heisenberg on Z3?
No, that's a different question. So for example, if we take villain model in Z3, there are vortices. So in that sense, the vortices also impact the fluctuation, but at low temperature, they are not strong enough to kill a long-range order. So in that sense, it's a bit different from here. For the Heisenberg model, the vortices, so physicists call those, I think, skyrmions and instantons, and then it gets closer to Yang-Mills type of things. I'd be very happy to understand more about those, but I think what they're basically saying is that there are many further randomness on top of a Gaussian free field, which would be in the tangent space of S2. And there are so many of those, but I don't exactly know what those are, that there is always exponential decay in 2D.
But there, you are thinking about the full turn or more things that happen in the Lie algebra somehow?
All doors open. I don't know. In this website, there is a picture of a skyrmion. But the picture is very is beautiful and is even very easy to understand what they mean. It's basically a ground state. It's basically the best spin wave along the S2 sphere. But how does this picture goes into this business? I don't know.
So typically we say that the model is critical when the decay of correlations is polynomial. But in this model, you somehow have a whole line of polynomial decay. So do you see, do you consider the model to be critical everywhere along this line?
Yes, so that's a very good question. So I think I think that's what they say, that there is a CFT everywhere along this curve. It could be that the CFT is always a CLE4 type of CFT, though the exponents they change along the curve. Because of this, it has never been completely clear to me whether the free energy would still be analytic along this curve. It could be that it's just C infinity everywhere because it goes from a critical to another. So I think there is some reasonable convincing evidence that this is analytic, but because of that, it's not completely, I wouldn't bet on it, for example.
And regarding those analytic questions, if you add a field in whichever direction, and then you look at the analytic properties in H, in the strength of this field, I guess in the subcritical regime it should be clear that it's analytic as a joint function of beta and H. That would be my guess at least. And but it's less clear to me whether it should be analytic as a function of H also on the critical around around beta above the critical temperature 0.
Okay, so that's a good question. So you're saying that if I fix beta large, then there are Lee-Yang type of analyticity. But if you want a joint analyticity of those two things, it's an even harder question than what I just discussed. It could be that this analyticity is just too much to ask. And that would be very nice, actually. That would explain maybe that there is a whole line of critical points. But that I have no clue.
Yes, if there's no more questions.
I'm
sorry, one more.
So there's also this thing where so I read it or heard this somewhere that you have the pair binding, unbinding, but then there's also something going on with four vortices or 6 or 8.
Yes.
So is this something we can see in this Coulomb gas, or it's something more in the continuum or not?
So yes, so I think there is if you go to the high temperature Coulomb gas in the continuum, so in works of Jeanne Boursier and Silvia Serfati, they do spot that at some point the partition function in the continuum, you have point-like Coulomb particles, start diverging when you have dipoles forming. But this is not yet the BKT point. They can go further, and at some point quadrupoles pop in, and then you can go further. And it's at the moment where you have 8 poles, 10 poles, and all the even integers you like, that all start contributing, that you reach the critical point, below which you have those power law decay if you were to still see the lattice. So all those start showing that there is some clustering starting, and at the moment everything is willing to cluster together. It's this real strong binding phase of BKT. So when you start only have some effect of the pairs, this is not yet the low temperature phase here.
I see. Thank you.
Okay, well, thanks again, and